Welcome to this explainer. All right, let's just dive right into some absolutely fascinating new research from Alibaba that tackles, without a doubt, one of the biggest bottlenecks in artificial intelligence today. We're looking at a brand new paper from the Qwen large model application team, and it explores a profound shift happening in how we actually train large language models. We are finally moving away from that heavy, manual, human-driven data annotation phase, and we're stepping into an era of interaction-driven self-evolution. But, as you can probably guess, as this transition happens, developers are hitting a massive roadblock. So, here is the billion-dollar question. How exactly do you teach an AI when it's already smarter than its human teachers? I mean, this is the ultimate roadblock right now at the cutting edge of AI development. When a model surpasses human capability in specific, highly technical domains, relying on humans to annotate data just isn't a viable way to improve it anymore. This reality is aggressively pushing researchers toward a new frontier, where models literally have to teach themselves, no external supervision. They have to generate their own tasks, find their own solutions, and then, critically, evaluate their own outcomes. Now, to really wrap our heads around how an AI evolves completely autonomously, we first need to define a concept called self-play. Think of it as the machine learning equivalent of playing chess against yourself to get better. The AI basically takes on different roles, generating tough challenges as one agent and then trying to solve them as another. By doing this over and over, it continually updates its own internal policies through what's known as multi-agent reinforcement learning. And honestly, this technique has shown some surprising serious power across logical reasoning, search, and coding tasks.
Which brings us to Section 1, the AI evolution dilemma. As these models attempt to self-improve without us watching over their shoulders, they hit a giant structural wall.
We are basically stuck in a massive Goldilocks dilemma right now. On one side, we have environment-bound training. This means you lock the AI in a very strict simulator, like a rigid math checker or a code execution environment. Now, this gives the AI incredibly precise, reliable feedback, but it severely restricts its learning to incredibly narrow domains. It just can't generalize to the messy real world. On the flip side, we have open-ended generation. This lets the AI synthesize any broad task it can dream up. It expands the task space beautifully, but it completely lacks reliable verification. The data it generates becomes totally chaotic and messy.
Usually, developers try to clean up this open-ended chaos using something called post hoc filtering, which is basically just checking the AI's work after the fact. But the problem is, this just acts as a passive sieve. Sure, it might catch glaring formatting errors, but it lets all these subtle residual logic errors and poorly framed tasks slip right through. And over successive training iterations, those accumulated errors act like a virus, causing what researchers ominously call synthetic data collapse. It completely fails to proactively guide the AI to generate tasks that are both logically valid and diverse.
So how do we fix this? That takes us to Section 2, Introducing Skills Self-Play. The researchers needed to find that elusive, just right middle ground.
Alibaba steps in with their solution, Skill Self-Play, or Skill SP for short. It's a brilliant coevolutionary framework that perfectly blends structured verification with open-ended exploration. It ensures you get that deep, verifiable execution within specific scenarios, but it uses dynamic routing to maintain a massive open-ended variety of tasks. It finally bridges the gap between structured accuracy and limitless exploration.
The magic here is all about agent skills. You can think of an agent skill like a perfectly organized, highly modular textbook that the AI can pull off the shelf and load up exactly when it needs specialized knowledge. Usually, if you stuff a ton of historical training data into a single prompt, you get massive context bloat. But here, skills neatly package expertise into self-contained units. They bundle the instructions, the rules, and the validators all into one clean, reusable interface.
Moving on to Section 3, Proposer, Solver, and Controller. The real key here is understanding the mechanics of how this ecosystem orchestrates the self-play loop to continuously train itself.
Okay, let's break down the mechanics. It's really helpful to think of this like a biological ecosystem with three main actors driving a continuous cycle. First up, the proposer. Guided by the skill library, the proposer acts as the teacher, synthesizing highly targeted, challenging tasks. Second, we have the solver. The solver acts as the student, exploring candidate solutions and trying to resolve the tasks, pushing its own capability boundaries in the process. And finally, the controller. The controller analyzes the student's test results, the actual execution trajectories, and feeds that data right back to the beginning to constantly update the curriculum.
And instead of just, dumping old test results into some massive log file, the controller actively manages this library in a continuous evolutionary cycle. It automatically refines existing skill packages based on execution feedback. If a skill becomes obsolete or redundant, boom, it prunes or archives it. But here's the coolest part. When the AI successfully explores an open-ended problem, the controller actually induces entirely new skills from that exploration. It distills scattered, noisy experiences into compact, reusable units, ensuring the AI's curriculum is constantly expanding without ever bloating the system.
This brings us to Section 4, Riding the Learning Frontier. Let's see how all of this builds into an intuitive mathematical approach to difficulty. Now, take a really close look at the diagram we're showing here because it illustrates this concept perfectly. This maps out what they call the learning frontier. You'll see a bell curve representing the solver's success rate, moving from a 0% success rate on the left all the way to a 100% success rate on the right. If a generated task is too easy, pushing toward that success rate of 1 on the far right, the AI learns absolutely nothing. It's just repeating what it already knows. If it's too hard, down near 0 on the left, it fails entirely and gets stuck. But look right in the middle at that green target zone at the peak of the curve. That is the learning frontier, where the success rate is roughly 0.5 or 50%. Skill SP achieves this by dynamically routing tasks, pulling from the skill library on the right to perfectly calibrate the difficulty of the task it hands to the solver.
Because of this setup, the proposer, our AI teacher, is always giving the solver a test that is just challenging enough to stretch its capabilities without totally breaking it. To build this perfect curriculum, the system evaluates all the generated tasks, verifies them, and then ranks them by a frontier reward. It essentially constructs a custom training pool from the highest scoring tasks, ensuring the AI is constantly operating right at the razor's edge of its current capabilities.
Let's look at the real-world impact in Section 5, Breakthroughs in AI Performance. Why does this theoretical framework actually matter for the smart agents we rely on? Okay, the data on these radar charts is honestly staggering. We're looking at the Qwen 3.4b Instruct model's performance here. Notice that solid red line? That represents the AI trained with skill SP. On the left chart, which measures tool calling capabilities across various benchmarks, that red line completely envelops the dashed lines representing both the base model and standard unguided self-play. It's a massive upgrade. But look at the logical reasoning chart on the right. This is where it gets crazy. The red line of skill SP creates a huge footprint of capability, while the unguided self-play method literally flatlines at the center. It isn't even visible. Without these structured modular skills, the unguided model fundamentally could not synthesize valid logical puzzles, resulting in a flat 0 score.
To put some hard numbers to those visual charts, we are talking about massive absolute performance gains of up to 42.9 points on major tool use benchmarks. That's not a small bump. It decisively proves that embedding procedural knowledge into modular skills vastly improves an AI's ability to actually utilize external tools accurately.
And for complex logical reasoning, we're looking at a 12-point turnaround on the Zebra Logic benchmark. That's huge because, as we just saw, this is an area where unguided, open-ended models just produce chaotic noise and fail. Skilled SP provided the exact structural anchors the AI needed to teach itself complex, multi-step logic. Now, check out this line graph tracking tool call accuracy, because it proves this isn't just a one-off fluke. We're tracking 2 different benchmarks here across 5 distinct self-play iterations on the bottom axis. You can see the accuracy starting quite low at iteration 0, but then look at the slope of those lines. They climb sharply and consistently sustain that upward growth across iterations 1 through 5. The AI literally just keeps getting smarter with every loop. It's concrete visual proof that this co-evolutionary cycle of proposing, solving, and skill updating is a highly robust, sustainable evolution engine.
The researchers really hit the nail on the head when they concluded that this framework represents a fundamental paradigm shift for the entire industry. By abstracting raw experience into reusable, co-evolving skills, they finally bridged that painful gap between structured, verifiable accuracy on one hand and limitless, open-ended exploration on the other.
So as we wrap up this explainer, I want to leave you with this thought to consider. Think about the sheer scale of the future this unlocks. If an AI can continuously map its own learning frontier, induce its own specialized skills, and infinitely generate its own perfect textbooks, what are the limits of artificial intelligence? We are rapidly entering an era where human instruction is no longer the ceiling, but merely the starting line.